All right, so going back to the example that we were working on before, the examples, x, oh, sorry, I misread it. This is x cubed. I kind of like a payoff to that, so let's make it x squared. Because we just did 2 examples like that. I want to show you how to actually get to the exact value. So, first thing I need to do is figure out my delta x. All right. B minus a over n. B is 2, a is 0, n is n, so 2 over n. All right. Then I want to come up with a general expression that represents the position along the x-axis. For that, we use the expression a plus I delta x. If you're starting off with a, and you're moving I movements in terms of delta x along the x-axis, that'll get you to any position of an important point along the rectangle. Or, I'm sorry, along the region corresponding to a rectangle. All right. So, a is 0. I we want to keep variable because we want it to be any I. I want this to allow for me to be at any position under the curve. Delta x is 2 over n. All right, next up is to find or to evaluate the function. And I might as well simplify that. 2i over n. Evaluate the function. And it's y equals x squared, so square this. All right, so I'm just squaring my a plus I delta x. All right. Then I have to multiply that by delta x. And that'll give me the area of any arbitrary rectangle under the curve. Go back to red. So I have 8i squared over n cubed. Right. So then, really, if you think about this part of it represents the height of any rectangle. The delta x represents the length of the base of any rectangle. Multiply the two together, you have now an expression that represents the area of any arbitrary rectangle under this curve. If I know which rectangle I'm looking for, the 10th, the 20th, the 300th, whatever, that's the I value, that's the position. And if I know how many subintervals there are in total, I would now know the area of a single rectangle. But the thing is, I want to have all of them. I want to add them all together over the interval. So what I want to do is find the sum of all that. All right, so then the question becomes from what to what? So we need an index, and this goes back to last night's homework. We need an index, a starting point. I equals 1. We want to go from 1 to n. All right, I want to start with the first rectangle and go to the nth rectangle. Now that's a bit of a conceptual piece because the left rectangular approximation starts with 0 and goes to n minus 1. If you come in, this is the part that I skipped, if you come in from the right, you would start with an I value of 1 and end up with n. Right? But as you apply limits, they both end up giving you the same amount. They give you the same quantity. So it actually doesn't matter which direction you come from. as long as you're applying a limit, right? So if you're doing it numerically, you just follow whatever the instructions are. But if you're doing it for the purposes of applying a limit later on, then it really doesn't matter which direction you're coming from. The reason I chose I equals 1 to n is because that corresponds with some of the rules that were on the homework from last night, which we'll get to in a second. All right. Now, this summation is in terms of I. So that means that the only relevant variable in this summation is I. What that tells me is that everything else can come out. They don't need to be there. So I could rewrite this as 8 over n cubed times the sum from I equals 1 to n of I squared. If you're going to get jammed up, this is where it's going to happen, because everything else is procedural. You just study the process. This is the rule. All right, I'll show you where it is. In theory,